Welcome to This Explainer. Okay, I want you to imagine trying to understand the shape of our entire universe. But right before you start, I force you to throw your rulers, your tape measures, literally all your measuring tools straight into the trash. Trying to understand geometry without ever being able to measure the exact distance between two objects sounds totally impossible, right? Well, today we are exploring a fascinating challenge: how mathematicians define spaces, shapes, and movement entirely without physical measurements.
So let's dive right into this. The ultimate mission of our source text today is, honestly, a massive one. It's trying to formalize our most intuitive concepts of reality. I mean, we instinctively know what it means for two things to be close to each other, or for a movement to be smooth and continuous. But how do you rigorously define proximity and continuity when the whole concept of measured distance has been completely stripped away? That right there is the absolute magic of general topology.
Here is our roadmap for the journey. We'll build these abstract concepts up logically, step by step. We're going to start with the foundational rules of topology, then move into proximity without distance, redefine continuity, track how sequences behave, and finally, unlock the sheer power of compactness. Let's get started.
All right, part one, the rules of topology. Let's figure out the absolute minimum rules we need to define a space. Because before we can explore a mathematical space, we have to actually build it. And it turns out we really only need these three simple, completely non-negotiable golden rules to create a topological space out of any set. Let's just call it set X. First off, our collection of open sets must include the empty set and the entire set X itself. Second, if you take any number of these open sets, we're talking even an infinite arbitrary amount of them, and mush them together, the result is still an open set. And third, if you intersect a finite number of these open sets, that intersection is also an open set. Oh, and finally, the exact opposites or complements of these open sets, we just call those closed sets. That's it. Those are the foundational building blocks of our new reality.
Now, what's really interesting about this is what happens when we push these rules to their absolute limits. We hit two wildly different extremes. On one end, you have the trivial topology. This is the absolute coarsest way to view a space, where the only open sets are nothing at all, or literally everything all at once. It's like looking at the universe with your eyes closed. On the exact opposite end, you have the discrete topology. This is the finest possible view where every single subset, no matter how small, is considered an open set. Every other topology out there, including the one that governs the standard real numbers we use every day, sits somewhere on the spectrum between these two fascinating extremes.
Which brings us to part two, proximity without distance. So, now that we have the rules of our space down, it's time to figure out how to actually navigate it. Think back to how you were probably taught geometry or calculus. You learned to define closeness using a circle, or a measured ball with a very specific radius around a point. But in a general topological space, the source text reminds us that the definition of a measured ball has absolutely zero equivalent. None. Traditional geometry's exact distances are utterly useless here. So, how in the world do we know if two things are actually close to each other?
Well, we solve this profound problem with a brilliantly simple idea: the neighborhood. This is the crucial bridge. This is what replaces metric distance. You see, you don't actually need to know exactly how far away something is. You just need to know if it sits within a neighborhood of a point. A neighborhood is simply any set that contains an open set, which in turn contains your point. It's how we determine what surrounds a point and what is local to it without ever having to pull out a ruler.
And just look at what this single elegant concept of a neighborhood lets us do. It's like a master key. We can determine the interior of a shape simply by finding points where the shape itself acts as a neighborhood. We can define the closure, which is basically the tightest closed skin wrapped around a subset. We can define a dense set, which is a subset so thoroughly, completely spread out that its closure is the entire space itself. And we can find the exact boundary. Think of it like the skin of an apple, just by taking the closure and subtracting the interior. All of this just from the idea of a neighborhood. Now, to make sure our space isn't just some blurry, inseparable mess, we rely on what's called a Hausdorff space, named after the mathematician Felix Hausdorff. The crucial point here is that this is a topological space where, if you have two distinct points, you are guaranteed to be able to draw totally separate, non-overlapping neighborhoods around them. It ensures that points can actually be separated from one another into distinct bubbles, which keeps the space mathematically predictable and well-behaved.
Moving right along to part three. Redefining mathematical continuity.
Okay, we have our spaces and we have our neighborhoods. The next logical step is to figure out how things move or map continuously from one space to another.
In standard calculus, you prove continuity using microscopic, exact distance measurements, right? You measure a tiny change in the input and prove it result in a tiny change in the output using those famous epsilons and deltas. But remember, we threw our rulers away. How do we translate that traditional idea of a smooth, unbroken curve into this highly abstract world?
And this brilliantly illustrates the power of topology. It redefines continuity completely backwards, relying only on sets. A function is continuous if the inverse image of every open set is an open set, or equivalently, if the inverse image of every closed set is a closed set. That's literally it. No measuring tiny microscopic gaps, just a flawless, elegant rule about how the function maps the fundamental structures of the space backward.
And because of that incredibly clean property we just talked about, we get the composition theorem. It essentially says if you stack two continuous functions together, mapping from space x to space y and then to space z, the overall journey remains totally continuous. The unbroken mapping of open sets backwards maintains its flawless structural integrity the whole way through.
That leads us to part 4, sequences and cluster points. Now let's introduce some real motion. We're going to look at how a sequence of points behaves as it travels through these newly defined abstract spaces. And to do this, we are going to reapply our trusty neighborhood tool. A sequence of points converges to a limit if, no matter what neighborhood you draw around that limit, the sequence eventually enters that neighborhood and never ever leaves. It essentially gets captured by the local proximity of the destination point.
1. That is exactly how many limits a converging sequence can have if you are operating inside a Hausdorff space. Because our Hausdorff space lets us isolate distinct points into those separate bubbles we talked about earlier, it turns out a sequence can't permanently settle in two different places at once. There is exactly one unique limit. Absolutely zero ambiguity. But, sequences aren't always perfectly well-behaved. Sometimes they bounce around a bit. That's why we have to differentiate a strict limit from a cluster point. A cluster point is a spot where the sequence enters its neighborhood infinitely often, even if it leaves again. Now, this might sound completely chaotic, but it reveals a beautiful hidden structure. Because hidden inside all that chaos, smaller subsequences are actually converging right at that cluster point. It captures the idea of points accumulating, even when things seem messy.
And finally, part 5, the power of compactness.
We have arrived at the final, and frankly, the absolute most powerful concept in this entire explainer. The ultimate constraint you can place on a topological space. Compactness. Now, the official definition is kind of dense. It says a Hausdorff space is compact if every open cover admits a finite subcover. But what does that actually mean in plain English? Well, imagine trying to blanket your entire space with overlapping open sets. If the space is compact, no matter how many infinite tiny sets you use to cover it, you can always throw away most of them and still cover the whole space using only a finite number of them. Essentially, compactness means a space is tightly bounded. It cannot endlessly escape out to infinity.
Let's move on and see how this builds, because compactness is basically a golden ticket for mathematical good behavior. It gives us incredible guarantees. If a subset is compact, it is automatically closed. Even better, if you take a closed subset sitting inside a compact space, it inherits that compactness. And crucially, in a compact space, you cannot have a sequence that just wanders off forever into the void. Every single sequence is absolutely guaranteed to accumulate somewhere and have at least one cluster point.
Compactness basically acts as an inescapable trap. Let me explain. If you have a sequence in a compact space, and it has exactly one unique cluster point where it gathers, the constraints of that compact space are so remarkably strong that the entire sequence is essentially forced to converge to that one point. There is simply nowhere else for the infinite sequence to hide.
And amazingly, this incredible power of compactness actually survives being transformed. Just think about the logic here for a second. Take any compact topological space. Transform it by applying any continuous map into another Hausdorff space. Because of how elegantly continuous functions handle open sets, the resulting image that comes out the other side is absolutely guaranteed to still be compact. The structural integrity is perfectly, flawlessly preserved across the entire transformation.
So we've completely rebuilt our understanding of how mathematical objects relate to one another, and we did it without a single ruler or measuring tape in sight. We replaced rigid, real-world distances with fluid neighborhoods, and we discovered the beautiful, inescapable constraints of compactness. It really leaves you wondering, if we can perfectly define shapes, continuity, and limits while stripping away all our physical measurements, what other hidden foundational truths of our universe can topology reveal?
Thank you so much for exploring this fascinating topic with me.